Okay, thank you. So when I was invited to give this talk, I was sort of picturing the audience would be almost entirely mathematical general relativists who hadn't worked in quantum field theory and curved space-time. As I discovered last week, there are an awful lot of people here who are working in quantum field theory and curved space-time, and there are a lot of experts. But this talk is directed primarily to the people who do not have a lot of expertise in working in quantum field theory and curved space-time. And what I want to do is give an overview of the mathematical framework of the subject. So might start by saying what it is. It's a theory where matter is other fields besides the metric. That's treated in accord with the principles of quantum field theory, which I'll explain to you about. But the important thing is that gravity is treated entirely classically according to general relativity, where it's a space-time metric, is what's describing gravity. So, this is certainly not expected to be any sort of exact theory of nature. On the other hand, it ought to be a good approximation to describe situations where the quantum effects of gravity itself don't play a completely dominant role. And I think it's fair to say that although gravity is being treated classically, there's no question that this has provided us some very deep insights into the nature of quantum gravity, most strikingly the prediction that particle production occurs in the vicinity of a black hole. That certainly has a lot of implication about the quantum nature of black holes. But I'm going to be primarily concerned here not with the physical applications of quantum field theory and curved space-time to things like the Hawking effect, but the sort of conceptual and mathematical issues. And by going to curved space-time, as opposed to the flat space-time versions of quantum field theory that are otherwise normally considered, it really forces one to take some new viewpoints, because crutches that are used, I think probably misleadingly and inappropriately as a basis for many ideas in quantum field theory and flat space-time, particularly the notion of Poincare invariance, global notions of energy, and most importantly, the unique existence of a Poincare invariant vacuum state. You don't have those things, and ability to take global Fourier transforms, you don't have those things in curved space-time, and that forces you to think of quantum field theory and curved space-time in a purely local kind of way in terms of the quantum fields. So just to get things started, I'll say one slide about the structure of classical physics, one slide about the corresponding structure of ordinary quantum mechanics. Then we'll look at the harmonic oscillator in quantum mechanics, and then very quickly move on to the quantum field in flat space-time. So I'm putting this up mainly to draw quite a contrast to the nature of the structure of the physical theories from the classical viewpoint and from the quantum viewpoint. In the classical viewpoint, the states of a system are points of some 2n dimensional manifold called phase space. Observables are just functions on phase space, and the key structure of phase space that one has is a symplectic form, a non-degenerate closed two form, which is in many cases, that structure is automatic because the phase space is expressed as the cotangent bundle of some configuration manifold. And one gets from this structure a algebraic kind of structure on observables given by the Poisson bracket. If you take the inverse of the symplectic form and apply it to the gradient of two observables, that defines its Poisson bracket, which is some other function on phase space, so some other observable. So that gives an algebraic structure on observables. And finally, dynamics is, in Hamiltonian mechanics, is described, which I'm talking about here, is described by providing a Hamiltonian function, and the vector field that you get by using the inverse symplectic form to raise an index of the gradient of the Hamiltonian, the integral curves of that define the dynamics. So that's really very different from what happens in quantum mechanics. The states now are described by vectors in some generally infinite dimensional Hilbert space, so not very phase, structure quite different from phase space. I mean, we'll be revisiting this as a kind of foundation of quantum mechanics shortly, but for now, this is what you'll certainly find in textbooks. Observables are now self-adjoint operators on this Hilbert space, and the one major connection between this quantum physics structure and the classical physics structure is this Poisson bracket commutator relationship. Commutation relations of these self-adjoint operators are supposed to reflect the Poisson bracket structure in this way. You can't do this for all observables, but for, observables linear in the momentum and or just functions of the momentum, arbitrary functions of the configuration variable, you can certainly do this. So the Hamiltonian is now an operator, a self-adjoint operator. It thereby generates a one-parameter unitary group, and that's how dynamics is now defined, and you can think of this unitary group as acting on the states, but it's actually much more convenient to alternatively describe it as, this is referred to as the Heisenberg representation of the dynamics, as letting the states be thought of as fixed and letting the observables correspondingly be acted on by this unitary operator to define the dynamics. Okay, and I put hats on here just to distinguish things but from the classical case, but I won't be talking about the classical case from now on. So I'm going to drop the hats. So everything here would have had a hat if it were on the previous slide. And the key to basically understanding what's going on, at least for a free quantum field, is to understand what's going on for a quantum harmonic oscillator whose Hamiltonian in terms of momentum and configuration coordinate Q is what I've written down here. And the structure of the Hamiltonian is really enormously elucidated by introducing this complex linear combination of Q and P, known as the lowering operator, or in quantum field theory will be known as the annihilation operator, which satisfies, just by virtue of the Poisson bracket commutator relation between P and Q, satisfies these commutation relations with themselves and this commutation relation with the Hamiltonian, which shows it as a lowering operator, because if you have an eigenstate of the Hamiltonian, A applied to that eigenstate will lower the will also be an eigenstate, but of lower energy. And now, if you, go through the dynamics of this and work in the Heisenberg representation, go back and find the behavior of this configuration observable, it's given in terms of the fixed Schrodinger annihilation and creation operators by this formula, where you've got sort of positive frequencies associated with A and negative frequencies associated with the so-called raising operator. So the Hamiltonian is bounded below. There will be a ground state, which will necessarily be annihilated by the lowering operator, since you can't have an eigenstate of lower energy. And you can obtain all the other states of the harmonic oscillator then by applying the raising operator to this ground state. Okay, so this is related to quantum field theory in flat space-time. If, let's say, the theory of a Klein-Gordon field in particular, that's what I'll, for definiteness, explicitly consider, but there's nothing, I'm not, I'm certainly going to be using the wave character of the equation of motion, but not really anything much else. And let's do this on a 3 torus instead of, for space, instead of R3, just to avoid, awkwardness. This is just for pedagogy in terms of what's going on. Well, if we break this field up into spatial Fourier modes, and I put it in this box just to have discrete modes and be able to use, sums rather than integrals. Well, I didn't write down the Hamiltonian for this, but it's should not be surprising that the Hamiltonian translated into these Fourier modes is of this form, which is just a sum of independent harmonic oscillators, just like the Hamiltonian I had for a single oscillator. So a free Klein-Gordon field is nothing more than an infinite collection, and the infinite is going to be very important here, because there really wouldn't be anything much to do or say if it was a finite collection. So if I want to know, this Heisenberg field operator is clearly going to be a key observable in the quantum field theory, and if I want to know what that Heisenberg observable is, well, I already gave you the formula for a harmonic oscillator, and in terms of these fixed Schrodinger annihilation and creation operator, this is the formula you get for what the quantum field is. Okay, but now something interesting happens, because this does, if you try to make sense of this at a point t, an event tx in space-time, there isn't any sense in which this right-hand side, the infinite sum on the right-hand side, converges. So this formula doesn't make sense, but if you write down a version of this formula where you smear both sides with a compactly supported test function, in other words, you use the version of this formula, but with an integral of f, with this f taken inside, that is perfectly well defined. So remarkably, for this free quantum field in flat space-time, one can make sense of what the field is and what it's doing, but you have to interpret it as a distribution. And that's the origin of all of the mathematical difficulties in quantum field theory, because you want to take nonlinear functions of the field. You may want to consider, even for a free field, nonlinear observables. But if we're doing interacting fields, even if we're just trying to do that perturbatively, the interactions, are nonlinear, and we've got to make sense of nonlinear functions of the field, and that's not so obvious how to do that if these are distributions. So there are funny words that are put on these harmonic oscillator kind of states when you're talking about quantum field theory. Well, so there's still a ground state of all of the simultaneously of all of the oscillators. I mean, again, we've got this, the only thing funny in this construction is the quantum field itself is now a distribution, but again, we can think of it as an infinite collection of oscillators. And this ground state has a funny name, like which is namely the vacuum, making people think there's nothing there. But of course, the quantum field is there, and the vacuum state is a state like every other state. So it's kind of a funny way of, well, I mean, it's a reasonable word and historically very reasonable, but anyway, again, we can get all the other states by applying these raising operators, well, and taking closures of spans of things of applying finitely many raising operators. If you apply n of these raising operators or creation operators to the vacuum, that's interpreted as having as an n particle state. So the notion of particles or whatever, well, it's a useful concept to introduce in quantum field theory and Minkowski, free quantum field theory and Minkowski spacetime. If you have interacting fields, then it is normally assumed that, for physically relevant interactions, that the late time descriptions that at early and late times, the states of the system look like states of some corresponding free field. So you can, if so, you can characterize the asymptotic in the past and asymptotic in the future states by particle states. And a lot of the focus in quantum field theory is on the S matrix that relates the incoming particle state to the outgoing particle state. And, this, well, a lot of good physics, has been done this way, which might really lead one to think that quantum field theory is a theory of particles, but that's very misleading, and when we get to curved spacetime, a very bad way of thinking about quantum field theory, but you can do it. Now, it isn't completely clear possibly exactly what we're using, but the key thing needed to get this sort of decomposition was really a time translation symmetry. And the notion of a particle is certainly dependent on a notion of time translation symmetry. Let me just mention here that if I look at products of field operators, now products of field operators at the same point are going to be problematic. That's a nonlinear distribution, but this is a bi-distribution. There's no problem with that, and the form of this bi-distribution is worth noting in the vacuum state as X and Y, well, this is true globally in flat space-time, but the important thing to notice is that as X and Y approach each other, this blows up as the squared geodesic distance between X and Y. Well, 1 over the squared geodesic distance is not a distribution. you need to put in these I epsilon and epsilon squared factors for me to tell you what this really is as a distribution. Okay. Yeah, and if we did a massive field, this is for the massless field, much very simple formula, there'd be another term with some function times log of this quantity appearing in this as well. Okay, so now let's move on to curved space-time. And if we were considering a stationary space-time, we can more or less just mimic what I showed you, in flat space-time, and there'll be, all space-times that I'm considering here are globally hyperbolic. There'd have to be a few other small conditions added to do this, but basically you can, there will exist a ground state that you can call the vacuum, and you can define particle states and so on. But one wants to do a lot more than that in quantum field theory and curved space-time. In particular, you might have some, cosmological space-time with no time translation symmetry and initial singularity, or you might want to consider collapse to a black hole. And if you want to follow the kind of program there of, you first start with a Hilbert space, if you're, a key notion in the construction of the Hilbert space was to define a vacuum state. The decomposition of the field operator relative to the vacuum state then could give you some Fock space that would have particles. But here now, in this much more general situation, you certainly don't have any preferred vacuum state around. You might try to look for one. I think this is about as good an idea of, people learning general relativity from having learned special relativity. You learn in special relativity, you've got these preferred global inertial coordinate. Before you learn finally that what you're really talking about is a space-time metric, which happens to be flat and have a lot of isometries in special relativity and is not in general relativity. You might formulate things in terms of global inertial coordinates, or the preferred coordinates, and formulate special relativity in terms of Lorentz transformations on global inertial coordinates. That's still how it's taught, amazingly. And then you get to general relativity, and so the first thing you look for, okay, what are the preferred coordinates in general relativity? Okay, well, that doesn't really lead to anything fruitful. Okay, and in a similar manner, I think you're not going to get anywhere trying to find a preferred notion of vacuum state or particles in a general space-time. But what you do have are these local, what you should have and what the theory is about are these local field observables. Now, not having a preferred vacuum state is not necessarily all that big of a problem for continuing to formulate things in the usual way. If a different choice of vacuum state gave you an equivalent theory, then you can make a choice or not make a choice. It doesn't really matter. But it's not hard to see that because of the infinite number of degrees of freedom, there are lots and lots of unitarily inequivalent Hilbert space constructions of quantum field theory in curved space-time. If you make different choices of vacuum state, you will in general get not just different particle descriptions or whatever of the same states, you'll get a completely different class of states that you're considering. You really get unitarily inequivalent theories. So how do you proceed without making a choice of vacuum state and thereby a kind of preferred Hilbert space representation of the theory? Well, there's an extremely simple and natural answer, which is to formulate the theory in the algebraic approach. So the idea is that one now really takes as the fundamental starting point, not that you have some Hilbert space of states and so on, but the fundamental starting point is that you have some, well, observables. Okay, we certainly have some observables, but they have some algebraic structure on them, which is primarily given by these commutation relations that I mentioned in the very beginning of the talk. So specifically for the formulation of quantum field of the Klein-Gordon quantum field theory in curved space-time, which is only going to attempt to describe observables linear in the field, so not phi squared things, but by distributions in phi. The idea is that one just writes down, well, defines a star algebra of observables as follows. You just write down the free algebra that you generate by writing down any, taking linear combinations of finite products of phi's of this form together with a unit element. And then you impose the following conditions. I mean, the linearity of the, you want this to be a distribution, so you certainly want it linear in F. We want the field to be self-adjoint, so if we allow smearing with complex functions, which would be convenient, we want, we don't have a Hilbert space here where we have a star algebra, but we want the star to satisfy this. Then we want the field to distributionally satisfy the Klein-Gordon equation. And finally, we want the canonical commutation relations to be whole. This is just the space-time version of the EQ, canonical commutation relations, that you would get if you, wrote this in wrote the classical theory in a kind of phase space formulation. So this is just what I've written down before, where this delta is the advanced minus retarded Green's function. So it's a homogeneous, it's a distribution that satisfies the homogeneous equation. So if we just factor this star algebra by these relations, by the ideal, generated by the relations, that is the star algebra that we want. Now, the observables then that we have in this algebra are, basically things of this sort. I mean, factored by these relations, so they would count as they would be normally described as correlation functions of the quantum field. Okay, now there's one thing that I think that is very difficult to understand on this slide, only one thing, which is this completes the formulation of quantum field theory in curved space-time for this free Klein-Gordon field, again, only considering observables linear in the field. So to explain, though, that, I have to tell you what a state is. that is a kind of missing ingredient. So in the algebraic viewpoint, a state is just a linear map from the observables into complex numbers, which satisfies this quite non-trivial, very non-trivial to check, certainly, positivity condition. This map is interpreted, or what you get over here is interpreted as the expectation value of the observable A in the state omega. So what does this have to do with states in the usual sense? Well, if we had a usual formulation where we had a Hilbert space and we had the quantum fields represented as operators, all of the observables represented as operators on this Hilbert space, then for any vector state in H, or really any density matrix in H, but let's just look at vector states, we're going to get a state in this algebraic sense by just taking the expectation value of the operator representative of A. So states in the usual sense of vectors in a Hilbert space that carries a representation of the field algebra are states in the algebraic sense. But, well, maybe surprisingly, if you hear it for the first time, but it's really remarkably straightforward and simple, if you have a state in the algebraic sense, you can construct a Hilbert space that carries a representation of A and a vector in that Hilbert space such that your original state is this vector. That's the so-called GNS construction, von Neymark-Siegel. And it proceeds as follows. Well, we need to get a Hilbert space. There's no candidate for even a vector space in the problem other than A. Where are we going to get an inner product? Well, the state itself is practically giving you an inner product. The only thing it's possibly failing to give you is you're only requiring greater than or equal to here. You're not requiring strictly greater when A is not 0. But this is practically an inner product, and if you just factor by the 0 norm vectors and then complete it, you'll get a Hilbert space, and that Hilbert space will carry a natural representation of the algebra, because the algebra knows how to act on the states, which are nothing more than algebra elements. And now if you look at the vector corresponding to the identity element of the algebra element, it's easy to show you get this. So every state in the algebraic sense corresponds to a state in the usual Hilbert space sense, and trivially vice versa. But now, if we formulate the theory in the algebraic approach, the sort of trivial algebraic approach that I've just described, we don't have to make a choice of Hilbert space. All I have to do is tell you what the algebra is, and that's completely described by this slide. And I've already told you what states are. And now you can choose any state you want, work with that. If you want, you can put your state into a Hilbert space that carries a representation of the algebra. You don't need to. I mean, maybe that'll be convenient for some. It's sort of like introducing coordinates or something like that. You know, if you're doing, you know, differential geometry on a manifold, you can do it if you want, and it may be useful to do it, but you don't have to do it. So that completely, well, that completes the formulation of quantum field theory in curved space-time if you're only concerned with linear fields and you're only concerned with observables in this algebra A. But that doesn't complete the talk and doesn't complete the subject, because you've got a lot of observables, even in the free case, that are nonlinear in these, classically are nonlinear in the fields, like the stress energy tensor, which is quadratic in the fields, and they're not represented in the algebra. And then you might want to do interacting quantum field theory. Well, that would be, quite a task to just do interacting quantum field theory. I mean, that may require some new ideas, but one knows formally how to do, perturbative rules for obtaining interacting quantum field theory results from free quantum fields. That requires, again, polynomial expressions in the field. Your interaction is polynomial, otherwise you're in a lot more trouble. But it also requires in the perturbative formulas there appear time-ordered products, and you've got to make sense of those as well. So what you'd like to do is enlarge this algebra of observables so that it includes at least all polynomial expressions in the field and all time-ordered products of these polynomial expressions. Then you've enlarged it to consider, you've got the stress energy observable in the algebra, et cetera, and then you've got all the quantities that you need to write down perturbative formulas. Okay, but that's, not completely straightforward. You could, try to define phi squared by a formula like this. Well, this right-hand side makes perfect sense when Fn is, a smooth function of compact support, or suitably smooth. But if you try to let this approach a delta function, which is what this is supposed to do, you're going to get meaningless divergent results in this limit. So this kind of naive definition of you just, take the product of distributions without doing anything to fix them up is not going to work. So for starters, one might, just try to define, this bracket is the same as the omega of the previous slide. You might just try to define the expectation value of phi squared. You want to do better than that. You want phi squared to be in a large algebra, and we'll get to that. But for starters, you might just try defining this. But if your state has a two-point function that is more singular at short distances than the Minkowski vacuum, it's not reasonable to expect this to be well defined. So you might just try to define phi squared for what are referred to as Hadamard states. And they're states where this two-point function, well, we're in curved space-time now, but, is as close to the behavior of the vacuum two-point function in Minkowski space-time as you can get. And indeed, I mean, back 100 years ago, Hadamard gave an algorithm for, it was designed, I've slightly adapted here with the I epsilons, but, designed for producing Green's functions in the Euclidean case initially and so on. But there is a procedure that will give you, a parametrics, if you cut this off suitably, or you could do other things to make an infinite sum with coefficients that are appropriately cut off from this, but an algorithm for defining this U and Vn in a, well, completely local algorithmic way that will solve the wave equation, you know, in each variable up to, you know, some term that goes to zero sufficiently rapidly as the points become coincident. So the idea is that you could try to define the expectation value of phi squared at x by starting with the two-point function in whatever state you wanted, subtracting off a locally constructed covariant Hadamard parametrics, and after you've subtracted this off, I seem to be missing well, okay, it's, of course, you do the subtraction and then take the coincidence limit. And this will give a completely satisfactory definition of the expectation value of phi squared, up to, of course, ambiguities in how you define this, and so on, which would correspond to addition of local curvature terms, which in this case would just be multiples of R. But we really want this as, you know, operators, not just as a sort of quadratic form. So we like to do better than this and really define this as an observable. Well, that's where, well, a breakthrough that was initiated by Radzikowski comes into play, which is the replacement of this very cumbersome Hadamard condition with an equivalent wavefront set condition. What this wavefront set condition is saying is that the singularities in this two-point function occur only when the points x1 and x2 are connected by a null geodesic. The k is tangent to that geodesic and future pointing, and the k1 and the k2 is minus k1 parallel transported along the geodesic to x2. And that's what this kind of symbol means. And as I'll explain, this will allow one to enlarge the algebra of observables to nonlinear observables and time-ordered products. I won't get in, especially since I'm starting to run out of time, into some of the historical things, but there are a few, well, interesting connections in that, you know, Hormander's original, you know, ideas that went into microlocal analysis apparently were initially attempting to, well, part of it at least was initially attempting to understand what the Feynman, what the status of the Feynman propagator was in curved space-time. So let me not sidetrack on that. Let me explain now how you can enlarge the algebra of observables to include nonlinear functions. And the first key step, well, is to introduce some Hadamard state. Well, you have to show they exist in an arbitrary curved space, globally hyperbolic curved space-time, but they do. And define, well, these so-called normal ordered products by suitable subtractions of the two-point function in a Hadamard state. So the normal ordered two-point function is just this minus this object which is in the algebra minus this two-point function in the Hadamard state times the identity. If you have, n of these factors, then you have the subtractions are a lot more complicated. You've got to consider every pair of points and suitably subtract things off. I won't write down the formula, but you can do that. So this is by itself is doing nothing other than changing the basis of the algebra to these normal ordered products versus the original, endpoint products. But now you can write down a formula for the product of two normal ordered things, which of course will, that product formula will encode the commutation relations that apply here. So you can, that product formula really just gives you all the information about the algebra. And now you can, if you look at that product formula, well, what comes into the product formula, will be things involving this Hadamard distribution, but you can see that the product formula will make sense when you smear not just with smooth functions, where this automatically has to make sense, but when you smear with an significantly enlarged algebra of observables. I mean, this is just using, when it makes sense to, take compositions of distributions with their wavefront set properties. And in particular, this distribution is perfectly fine to smear in with this object. So that defines, a normal ordered phi n, which is in this enlarged class of observables. But that normal ordered phi n is an imposter for what we really want, because this normal ordered phi n depends on, some choice of Hadamard state that we introduce to get things going. So this isn't doing us any good directly, but the idea is that we've made an enlarged algebra of observables that's big enough to find the things we want, which is this. All we have to do is write down what we're looking for, a list of criteria of what this phi n should be, including its commutation relations, and most importantly, including that it should be local and covariant in the metric, which this is not. And one can thereby prove that there exists a unique prescription for finding, phi to the n, let's just look at the simpler case of phi squared, which has some ambiguity in it. In this case, this is the ambiguity in defining phi squared, and that's an ambiguity that one will have to live with. It's a much more complicated analysis to follow through on the same program for time-ordered products. And there's a rather long list of additional properties that you need. I mean, the time-ordered product, once you've defined all these nonlinear observables, the time-ordered products of them should be just that string of observables in the right time order when they're smeared with wave functions that don't overlap each other. So this is a trivial problem in that regard. But the problem is if you want to consider time-ordered products of things smeared with test functions that do overlap each other, well, it's sort of a question of extending this distribution to the diagonals. That is what all of renormalization theory in the quantum field theory books is about, and that's, you know, not a completely trivial subject, but the idea is you can do it successfully in the curved space-time case as you could in the flat space-time case. So once you've done this, well, quantum field theory in curved space-time for free fields, including nonlinear observables, is well defined, and quantum field theory for interacting observables is perturbatively well defined, up to, well, renormalization ambiguities in the nonlinear observables themselves, which you normally would not consider in flat space-time, where you define this by normal ordering with respect to the vacuum. Oh, I'm probably running close to being out of town. I will finish up rather quickly. And up to renormalization ambiguities that include all the ones that you have in flat space-time, but also include you know, new ones involving, you know, ambiguous terms with curvature in them. Okay, so I just quickly mention, I think I won't ask how much time is left. I only have 2 slides left, so I will finish quickly, but I think this is worth mentioning. So up till this point, because I think this is a very interesting and completely unanswered question, I've been imagining that I've just fixed a space-time with, you know, some globally hyperbolic space-time with a fixed metric g, and I've defined the quantum field on that space-time. But really, within the context of sort of semi-classical ideas, one would expect that the space-time should be related to the state by this semi-classical Einstein equation. So only those metrics and states that satisfy this equation should be relevant. But it isn't clear how to make sense of this equation. I mean, we can make sense of this side, and we definitely can make sense of that side, so we can check if we have a solution. But if we're trying to do something like initial value problem, it's completely unclear what to do, and it's very likely that this equation, because effectively the stress energy tensor contains higher derivatives of the metric hidden in it. In the renormalization procedures, you can see that even the ambiguities in the stress energy tensor are higher derivative. It probably has a lot of spurious solutions, and it isn't clear how to deal with this equation in even a suitably approximate way. So I'm just throwing that out as an interesting issue, and let me conclude now. So what I hope I've shown you in this talk is that the theory of a free quantum field in a fixed curved space-time can be given a completely rigorous formulation with a well-defined notion of nonlinear field observables that's uniquely specified up to some local curvature ambiguities. And similarly, perturbative quantum field theory is as well defined as it is in Minkowski space, although there'll be additional local curvature ambiguities. What we don't have is a non-perturbative formulation of interacting quantum fields in curved, or for that matter, in flat space-time. And of course, gravity has been treated entirely classically in this whole procedure, and we don't have a quantum theory of gravity itself. Okay, thank you.